there are any stupid questions. So first of all, thank you for the invitation. I will try to explain in short the theoretical background which is lying behind the code, which name is Terminator. So because it was great, I have to give you. So basically, I will start from I have to first put some background, theoretical background, in order to people understand maybe more or less what the Terminator is used for and what is capable of. So basically, as it was already said in the previous talks, there is some need in the description for the description of the heavy ion collisions at ultra-relativistic energies, and basically there is some standard model which settled down during the last years, and this model includes three basic stages which usually have to be included in order to describe the data. And this is, of course, based on the phenomenological comparisons to the experimental data. So first of all, there is needed some initial conditions modeling. This involves modeling of colliding nuclei just already before the collision. Then there is some hard interaction between the constituents of the nuclei, and we have to model somehow the energy deposition of in these interactions in the volume of the interacting system. Then we don't yet know very well how the hydrodynamization somehow proceeds, but basically if we want to describe the data with the hydrodynamic equations of motion, this hydrodynamization phase is needed. And since the data more or less suggests that there is some hydrodynamic evolution, we need this stage too. So once we put the initial conditions into the hydrodynamic evolution, there is expansion and cooling according to the equations of motion. There is some phase transition needed from the quark-gluon plasma phase, because we start with ultra high temperatures and the system cools down to the hadron gas. So we need to model this somehow. And finally, there is a freeze-out, which is a, let's say, topic of this talk. So basically, I will try to explain how the freeze-out procedure can be performed in a simple perfect fluid hydro, and how it's implemented in Terminator. So in order to start with something simple, so that we all more or less know what I talked about, I start with non-relativistic ideal fluid dynamics. In this case, the fluid velocity, mass density, and the pressure completely defines our system. And then, using equations of motion, which we, I guess, all are familiar with, that is the Euler equation and the continuity equation, we just evolve the fluid. And in order to close this system and solve it numerically, there is some input needed, which involves the equation of state, the one which relates the pressure and the mass density. So, switching from non-relativistic to ultra-relativistic systems involves some, let's say, different definitions, way of defining our fluid systems. First of all, the mass density has to be in exchange with the energy density. since the kinetic energy of the system is large. Secondly, the form velocity doesn't transform properly under Lorentz transformation, so that's the reason why we have to exchange with something which transforms properly. And the last thing is we have to remember that the main assumption lying behind the usage of the perfect fluid hydrodynamics, that is the hydrodynamics of perfect fluids, is that the system is in perfect local equilibrium. It means that the system may be described with thermodynamic properties which are space-time dependent, and also the interactions in the system are strong enough to keep the system in the local equilibrium. So that the system not only is in the equilibrium at the beginning, but also it stays in this stage for the whole evolution. Having this, we can define the temperature and the form velocity, and the two can be somehow put it in one variable, which is the energy momentum tensor. The energy momentum tensor then has to be, in order to solve the equation, to obtain the equations of motion, it has to be follow the following conservation laws of energy and momentum. And finally, in order to solve them, we have to have any knowledge about the form of it in the perfect fluid case. So, in the case of static equilibrium, we know that the pressures have to be equal in all directions. That is what lies behind the idea of the perfect fluid. That is in the direction of x, y, and z, the pressures are equal. And this is how the energy momentum tensor looks like in the local respect of the fluid element. In order to obtain the form of the energy momentum tensor in a general frame, the most simple thing that we can do, we can just apply the Lorentz transformation and Lorentz transform it to the general frame. Finally, if we use covariant notation, we obtain its form in the following form. And finally, in order to somehow compare this, obtain somehow similar form as the ones in the case in non-relativistic case, we have to project these conservation equations on the space parallel and perpendicular to the form velocity of the fluid element. In this case, when you project on the direction perpendicular, you obtain the Euler equation, and of projecting along the form velocity of the continuity equation. The last thing is that you have to, usually you have to somehow parameterize the form velocity which enters this equation, and you parameterize it in such a way that you impose the form which involves the rapidity of the fluid. This procedure is suggested by the fact that there are relativistic energies, and at these large energies you have to somehow deal with the rapidities of the fluids instead of the velocities themselves. The last thing is, of course, imposing the relation between energy density and pressure, and this goes in a similar way as in the non-relativistic case, except in the case of the QCD system, we don't have much knowledge about the system. So basically, what we would like to do, if the system was described by the perfect fluid hydro, you would have to reveal the form of the equation of state. So by comparing our predictions from the fluid dynamical evolution to the experimental data, you would have to get knowledge about this form of the equation of state. The problem is that it's completely, let's say, hard to do. And in this case, what we can simplify is that we use the results from lattice QCD simulations done in the equilibrium, and then you somehow try to model your fluid at very low temperatures. Usually it's done with some concepts involving the hadron gas. Sometimes they may or may not involve interactions and so on. The experimental data suggests that there is a smooth crossover in the range of the transition temperature, the TC, critical temperature, which was mentioned already. So, so it's somehow, it doesn't agree with the previous expectations that actually there should be first order transition in this range. Okay. Once we have the equations of motion, as I explained, we impose the equation of state. We have to solve it on a computer. There is no way to solve these equations analytically, except for some very simple cases which doesn't tell us the whole story. So what we usually do, because of the more or less boost invariance in the mean rapidity, we use usually the so-called Milne coordinates instead of typical Minkowski coordinates. So that in the t and z coordinates are exchanged in favor of tau and eta, which are basically the proper longitudinal proper time and the space-time rapidity. Finally, in order to solve any such equations, you have to put some initial condition. This initial condition, of course, may be modeled in different ways. I assume, in this lecture, I assume something very simple, that is a smooth fireball, which is created according to some simple model. However, in general, this modeling have to involve some a priori calculations based on, let's say, calculations from the saturations model and so on, which were explained in the morning by Professor Radosław. This picture shows more or less how we decide, how we define our system, coordinate system in this evolution. So we assume that the direction of the beam, the eta direction, and the x direction, which is basically parallel to the impact parameters between the centers of the nuclei, span the so-called reaction plane. Then in the perpendicular direction, you have the y direction. Finally, the impact parameter is chosen typically according to the Lauber model. It's chosen to fit the number of participants in the experiments. Since, as it was mentioned before, you cannot actually control the impact parameter in the experiment. You just control the number of participants, and this has to be somehow transferred into the impact parameter. So having this knowledge, okay, I more or less explained what is already on this slide. So in order to get more knowledge, more, let's say, a priori calculations of the initial state for such evolutions, hydrodynamic evolution, you have to somehow go back to the Professor Radosław lectures. However, as I said, I use some simple parameterization, which gives you some kind of, this kind of fireball. The colors denote the temperature going from the higher in the center to the lower on the back to the surface, right? So finally, what I decided, what I was talking here about is the profile of the energy density of your firewall. However, there are not only these variables, there is also needed the information about the flow velocity of the fluid. And this is, since we don't have too much information on this, it is usually assumed that there is no flow in the transverse direction, so in the direction perpendicular to the beam. And since there is approximate boost invariance, we assume that the rapidity of the fluid is more or less equal to the space-time rapidity. That is, we assume more or less that the system at the very beginning is evolving according to the so-called Bjorken model. Finally, we have to put all of these equations on the computer and solve it numerically. Here is the example of such evolution. On the left, you see the evolution in the eta and x direction. You have a temperature with the colors are the temperature going from red, the hotter, to the blue, the colder one. And you can see that basically in the transverse plane there is this ellipsoidal shape. This ellipsoidal shape comes from the fact that this collision, which is presented on both of these figures, was done for the non-zero impact parameter. If you do such calculation for this case, you basically colliding the two nuclei which are not exactly overlapping, but they are somehow separated by the impact parameter. So that if you overlap two perfect spheres, you will obtain a kind of elliptical shape. And what you can see is that according to the evolution of the glaciers, you can see that the system cools down, it expands, and also due to this elliptical shape, there is more flow in this direction. You can see the streamlines which are somehow collected more here than here, and then when the system dilutes, the flow is more or less symmetric along the transverse. Finally, what has to be mentioned is this is not all of the whole truth. Actually, the nuclei should be modeled more like a composition of nucleons, and these nucleons, when collide, they don't have to form the perfectly symmetric initial state. So instead of having something like perfect ellipsoid, you get something like this, and even more, it doesn't have to be elongated along the y direction, which was in this case, the y direction was the direction perpendicular to the reaction plane, but it can be somehow rotated due to the randomness of the positions. But this was only a comment in order to keep some picture in mind. And all of this stuff which I was talking about somehow was prepared in order to come to this point, which involves the result of the system. In principle, in perfect fluid hydrodynamics, there should not be, the equations themselves should evolve any system down to zero temperatures, but of course it is not physical. The system, any system should, due to the matter dilution, you will get the case where the particles just travel apart, and since they don't interact, they just move freely, so they keep their previous momenta, which we can observe in the detector. So finally, we have to include the fact that due to the rapid expansion and the material dilution, there is a breakdown of the local thermal equilibrium, and we have to somehow model it. So we have to impose it in on top of the hydro evolution. So there are two concepts which are typically brought up. First concept is the kinetic freeze-out. The freeze-out which tells us that when the time of collisions becomes comparable to the expansion timescale, so basically the time of collision can be modeled as being proportional to the inverse of the density of particles and the cross-section of the particles. Both of these things are basically dependent locally on the cross-section, so they are dependent on the type of the particles that we want to describe, and they are dependent on the density, which can be inferred from the evolution equations. On the right-hand side, you have the expansion timescale, which basically involves the fact that the system, if the system is expanding very fast, the particles can go apart quicker than if it's the couple expanding slowly. So the kinetic freeze-out assumes that when these two timescales are comparable, all interactions cease. That means that they stop interact at this point, and they just, the momenta of all particles, they are frozen and they free stream to the detectors. The next concept is the chemical freeze-out. The chemical freeze-out involves the fact that it was observed at low energies that the inelastic cross-section is typically smaller than the elastic cross-sections. So there is less chance that the particles will create new types of particles, or for example, decay to some new types of particles, then the particles just scatter on themselves. Which means, if you look at this formula above, which means that the temperature of the chemical freeze-out should be higher than the kinetic one. This means that the inelastic collision cease and the particle abundances becomes fixed. This is due to the fact that you cannot create any more new particles. So, for example, numbers of pions, kaons, protons, and other particles are becoming fixed. After that time, if the temperature is below chemical freeze-out, they can only scatter elastically, so they can only change momenta, and that's all. It's important to keep these two concepts in mind and remember the ordering. So the whole, our point of view is easier in the following.
And just a short question, can you tell us two values, typical values of the thermal freeze-out and of the chemical freeze-out?
Well, the thing, okay, typically, I didn't come to the point, maybe I will continue and this will be clear because I have this one. So, what was found a couple of years ago, maybe even more than a couple, it was in 2001, Krakow group figured out that actually this is not the case. The two freeze-outs, at least this is what comparison to the data suggests, the two freeze-outs happen almost, and must happen almost at the same time. This was the result of the comparison of the models, which assume the following. There is, at some space-time point, there is a local and thermal equilibrium reached. It means that all the particle phase distribution follow the statistical ones. So, for example, the distribution of gluons are following the Bose-Einstein distribution. Then there is a change from fluid elements to the particles. This change involves not only the stable particles, but may also involve some unstable particles like heavy resonances. These, on the other side, on the other hand, can decay to heavy resonances, but lighter ones, and the whole situation may repeat. So there are some, let's say, decays which follow in cascades. But nevertheless, this change from fluid elements to the particles occur at some universal values of thermodynamic parameters. There are different ways of dealing with it. Some groups, instead of temperature, use the energy density and so on, but if you know the equation of state of your system, you can dial one to the other and so on. So let's say that we are talking about the freeze-out, which happens at certain temperature and the chemical potential. Then, if you assume that your system has to decay at this given temperature, out from the four-dimensional phase space, space-time, you just cut off the three-dimensional surface. It will be clear when I go further in the next slides, but this is basically the idea. You cut off some surface from your space-time. Then you generate hadrons on this surface. So whenever they cross this certain value of the temperature, they change into hadrons, and they just follow the following assumption. They just free stream, and they may decay into the resonances may decay to lighter particles. So the picture is that there is no interaction going the other way. You have a resonance which can decay to lighter particles, but the lighter particles cannot create resonances anymore. What was the result of these comparisons was the code which was written by the Krakow/Warsaw group, which was called Terminator, and it was basically applying this whole procedure which I talked about. So there are two codes, basically the old one, Terminator and Terminator 2, and basically the code is used to transfer the information from the hydrodynamic stage to the hadron stage. Now, how it's made in practice? So as I said, there is a condition that when the temperature drops locally below some freeze-out temperature, you extract some surface from your four-dimensional space-time, and you can see how it proceeds. The red curve here denotes the value of the freeze-out temperature, and the freeze-out temperature is fixed. When the proper time increases, so your evolution goes on, you just extract the values of the shape of the hypersurface. So it looks like this. You, instead of having the 3D evolution, I have no evolution along beam axis here. I just suppress this because it's not possible to show four-dimensional evolution here. But if you suppress it, instead of three-dimensional evolution, you get actually two-dimensional hypersurface here. What you do next? Then you somehow parameterize this hypersurface in such a way that the parameterization is not ill-defined. What it means? It means that, for example, if I have the surface like this, I basically would have the proper time as a function of x and y coordinates. However, if you look at this projection, you can see that there can be a case where tau is not a function of x anymore. So that instead of parameterizing tau as a function of the space-time coordinate, you parameterize it using some angle. And the same can be done in the transport direction. So this is just to be somehow to show you how this parameterization actually looks like. You have a space-time coordinates which are parameterized in terms of three angles, and this parameterization looks like this. And basically that's it. Once you have this space-time parameterization and you extract the surface, the question arises how to actually change the fluid elements to actual particles. And the basic idea is to look at the flux through the surface. So you take the definition of the particle flux in the kinetic theory, which is basically given by this formula, and you look what would be the flux through the unit element of the surface, which is this 3 sigma. And this is the n sigma denotes the number of particles crossing the surface, the elementary unit element of the surface. If you want to have invariant momentum of this distribution, you just differentiate it over momenta. And in order to have the momentum distribution over the whole surface, you have to, of course, integrate it over the whole surface. And basically, this leads you to the formula which is called the Cooper-Frye formula. And this formula is lying behind the generation of particles in terminator. So you basically follow this formula. This gives you some distribution how to generate particles having the surface. Going back for a while, we have to define what is actually the distribution, the phase space density of the particles which are actually crossing the surface. As I said before, you assume in this model, of course you can do some improvements, but assuming that your fluid evolves according to the perfect fluid equations of motion, your fluid is described by the thermal distribution. So basically, just before the freeze out, so just before the particle, the fluid elements cross the surface and they form hadrons, just before that moment they had thermal distribution. So we assume that this thermal distribution is frozen, and we observe the same thing on the other side of the surface. And in this case, you can just assume that this distribution has the Fermi-Dirac or Bose-Einstein form, depending on which statistics which particle statistics you are looking at. Now the question arises: what are these parameters which are entering the distribution? There is temperature, which we assume that it is constant on the surface, so it's just value of the freeze-out temperature. It's here. Then there is a chemical potential, and we, in principle, at LHC, we can assume that the chemical potentials are more or less vanishing. However, I will maybe explain this a little bit later, but finally there is 4 velocity of the fluid elements, and this 4 velocity is just extracted locally at the surface. So if you look at a certain point at the surface, you just look what is the flow extracted from fluid dynamics, and you just put it here. So according to this model, the fits which were done in the past involved fitting of the experimental data on the PT spectra of different particles, and these fits were performed involving all the possible decays known at that time in the PDG particle data group. And these fits show that actually this temperature and chemical potentials are having some values extracted from the fits, and they actually don't change much when you go from low to high energies. So for example, at RIC energies and LHC energies, these values of the freeze-out temperature and the chemical potentials, well, the temperature was similar, but the chemical potentials were lower because the energies are so energetic, the energies are so high that in the middle of the system, the baryon chemical potential is almost valid. Now the final comment, which somehow is not involved in the code itself, however, I think it's important to mention, is that this whole comparison with the experiments is done within the thermal models, which don't assume any evolution. So basically, you assume that you have a static fireball, and the system which is inside is basically following the thermal distribution, and fitting the data, you can find what are the values of chemical freeze-out and of the temperature of the freeze-out and the chemical potential. However, in the Terminator, except for this modeling, there is evolution involved. So the system actually evolves in space-time, and these values can change. Since, for example, when your system decays into lighter particles, so for example, you have heavy particles which decay in sequence, and then they populate light particles. These lighter particles, which basically populate the low PT part of the spectrum. This is due to the fact that there is less phase space available. Finally, the form of the fluid element is given by the let's say differential geometry. This is only mathematics, so you can find this expression in the book by Misner and Wheeler. There is nothing special about it. Having all these ingredients, you can basically calculate the product of the hypersurface element times the form momentum, and the form momentum times the form velocity, and you can put it in your Cooper-Frye formula. What is done next? You just implement this formula in the Terminator, and once you know the hypersurface, Terminator just proceeds according to the Monte Carlo procedure, generates the distributions of the particles according to a six-dimensional distribution which is given here. It doesn't really matter what are details. This is a six-dimensional distribution, and it's a complicated procedure. That's why it's imposed in a Monte Carlo way. I guess more or less I'm coming to the end. Final thing which I wanted to mention is that instead of using some hydroevolution, so instead of being able to model your system, writing down your equations of motion and proceeding complicated numerical simulations, you can actually learn from people who did it in the past. So, for example, performed some simulations and saw that, for example, the hydrodynamic models describe the system well, and can infer from their evolution what can be actual parametrization of the freeze-out. So instead of getting this form of the freeze-out, you can try to parameterize it by, for example, assuming that the proper time here is more or less flat here. So it's just a line as a function of the transverse coordinate. And actually this was done many times in different models. These models are called the so-called hydro-inspired models. There are two of them which are quite successful and used also recently by experimentalists. The one which is most important is the blast wave model. This model involves some parameterization of the force velocity in terms of the transverse fluid velocity and the form of the freeze-out hypersurface. The difference between these models, this model as it is implemented in Terminator, and the feats which are used by experimentalists is that in experiment you don't involve any resonances decay. Here you accept for generating stable particles, you also include the decays. So it's not a one-to-one correlation. There is also a Krakow model, which basically differs by a bit by the form of the force velocity and the shape of the Friesel hypersurface, but in principle the concept of this parametrization is similar. Finally, I would like to maybe discuss more how the decays are performed. So after generating the set of particles on the hypersurface, you allow them to decay. First of all, the process of generation is going according to the Scher tables. The Scher tables, in principle, are the tables which contain all the information about all measured and established resonances, all the hadrons, the details concerning the isospin, mass, and so on. And except that, for that, there are also tables which, this information is separated in two sets. One contains the information on particles, and the other set contains the decays of these particles. And these decays are used on the second stage. Once the particles are generated, the decays to the lighter particles goes along the data contained in the Scher tables, but the Scher tables on the decays. The decays go along the the decays go along the probability density, which involves the width of each state, and also the decays to 2 and 3 body. The 2 and 3 body decays are possible. Finally, the code, which was written in quite long ago already, is available online, and this whole talk is somehow prepared in order to teach you how to use it and to use it for your own purpose. So basically, in the next part of the lecture, we will try to teach you at least a bit of this. So the code needs the C++ compiler and the root installed on the machine. And to each of you, there were sticks given, which contain the operating system and some files which are the files of the terminator. There is additional PDF file which is available online. It's available on the website of the school. So basically, once you boot your operating system, you have to log into the, you don't have to log in, you just go to the website and download the handouts which were prepared for you. And I would suggest that you go through this handout with our help and try to learn more in practice how to use it, except for some for this introduction, which is more theoretical. I don't go further, maybe I will stop here and we can switch to practice session. Thank you.
Okay. Thank you very much. Before we move to the practical session, are there any questions?
Yes.
I wonder how this hypersurface depends on whether you have a phase transition or not, and how this can potentially influence that particle.
You mean the shape or its size?
The shape.
The shape. Okay, the shape. So basically, the size of this hypersurface. I mean, if it's larger, like farther put farther from the center of the system or closer. This depends basically on the equation of state. And of course, if it's more hard, then this shape is of course, this size is of course larger.
But the shape is important because if you look on the
Yes, the shape is.
the size will be the overall normalization presumably.
Yes, it's not only
But
normalization.
but the shape is essential for the distribution.
I think that the shape can be different, but it's a matter of details. So basically, what actually you would
But
be
you should get it
interested.
from, you should get it from hydrodynamical equations. I mean, if you calculate this
Yes.
surface
Yes,
from hydro,
you can extract
Then
it
you
and
put,
look at different
yeah.
equations of motion, equations of state, and see how.
It's crucial what the initial condition will be taken.
no, with the same initial conditions.
The same.
Oh, yes.
As we the same one.
Depends on inclusion.
So was it done? Have
I think probably it must have been done.
but there has to be some differences. The question is where they are. If you look on the PT distributions, they are maybe not so essential for the equation of state, but if you look more differential, maybe then you will see the differences.
This is what I'm not sure about, but I guess due to this, there were some studies involving comparing the size of the system. So basically,
The size is clear because
that
the
HBT,
lifetime of the
yes.
system then it will be.
yeah. So basically, this changes, but the shape of it, I'm not sure what is actually changed.
Pasi, could you comment?
Pasi?
Yes. First of all, look at the shape from however you calculate the evolution. Terminator doesn't know, Terminator doesn't care. It is something which is fed into.
Yes.
Second, all of these equation of state effects, you may see something in HBT radii. What comes to the PT distributions, forget it. How the equation of state is, or how the flow velocity is changed, you take it back by changing your freeze-out temperature. You don't see anything. Only thing I have seen to have any effect is the PT differential V2 of heavy particles, and even that will be washed away by dissipation. Now the Frankfurt group claims that by applying some artificial intelligence procedure, they can differentiate between first-order phase transition and smooth crossover. But what they have, at least so far, is rather artificial intuition, not intelligence. And I'm afraid that they can see it only because they have very different equations of state. Then when they start making the difference smaller and smaller, again this correlation will wash away, I'm afraid. So nothing to be seen there. HBT maybe tell you something.
Oh, I might have a just continue question to that. So how does that actually work with the first order phase transition? Would I evolve the fluid dynamical equations across the transition and follow the system just by following the evolution equations according to the equation of state, and then after I'm out of this binodal region, I start to apply Cooper-Frey, or how does one do that in practice?
It is equilibrium of first order. If it is there, I mean, it's equilibrium first order. So you do not see this binodal instability, of course, in this study.
Not even traces? Actually, that would be
You
good.
see traces that you have, I mean, you have to make a Maxwell construction, of course. So you see traces, I think.
If we apply Maxwell construction, then that is how you follow the system evolution. You get your well-defined equation of state, and you Cooper-Frey it when you want to do it. Then if you want to have this spinodal decomposition, then that's more complicated. But at least what Jan is telling us, if you start above the phase transition region, you won't see any effect. Then if you start in the middle or just above the transition, then you might see something.
Has anyone made a quantitative study?
Yes, Jan and Jörn, Jan Steinheim and Jörn Randrup.
Okay.
So So I was just referring to their results when I said that if you start at just above, then you may see something. If you start well above your phase transition, forget it.
All right. Any other list, please?
So is this hydrodynamic flow smooth, or can you develop some shock waves, things like that?
So basically, it doesn't have to be smooth according to perfect fluid hydro. You can develop some shocks, but at least you try to get rid of it, because quite quickly it will crash your code. So there are some dealings, ways of dealing of shocks in hydro, but all of them basically involve some generation of entropy. So, and this is somehow a way of, whatever way you do it, you will have to smooth it out using your algorithm. Yes?
But actually, I'm not asking whether there are discontinuities in hydro, but whether discontinuities actually appear in these problems. I mean, if you start with nuclei approaching.
Yes. Well, they might. I don't know if it's settled that if they are or not.
Okay.
There was a question about the shock wave at what stage of the evolution?
I mean, the hydrodynamical evolution in these heavy ion collisions, do you develop shock waves? During the hydrodynamical phase.
We usually use it only to describe the expansion stage only. And then we see shock waves if there is a sharp first order phase transition. Then you may have something called a rarefaction shock wave. But usually when we are dealing at trig and LHC energies, the assumption is that the equation of state is a smooth crossover, no shock waves.
Yeah, this was a problem in the early stages, early times when people were applying perfect fluid, having a first order phase transition. But this is, until now, I think it's all gone because people see that there has to be a smooth transition in the equation of state. And this somehow disappears in this case.
I mean, there were numerical instability, of course, if you have this first order phase transition. And then the first algorithm was developed in Frankfurt, actually. It was PhD thesis of one of the person. I think when it was passed in 1986 or something like that. It's so-called Shasta algorithm.
It was not developed in Frankfurt, no. It was applied in Frankfurt. Shasta is not Frankfurt invention. Original authors were Americans. They developed in the Naval Research Laboratory.
So it was coming from this.
Early 80s, if I remember right.
But this was developed for the non-relativistic hydro.
Yes.
And they have done it for a relativistic hydro.
The structure of the algorithm is such that it doesn't take a lot to see that it is a similar equation in a relativistic setting works. So if there's a shock wave, only problem is then applying an algorithm which can handle them. Otherwise, no problem.
Yeah, so basically it's an algorithm problem. But the physics itself rather suggests different scenario.
I mean, I still
Yes,
have
please.
a follow-up question to this first order or any kind of phase transition. I mean, what I will create are spatial correlations, right? And also momentum correlations. And I was wondering what happens actually if I then particleize my fluid. Do I actually not lose knowledge of these correlations by a simple Cooper-Frye freeze-out procedure?
You are losing correlation.
What happens to what?
My fluid develops, and if I pass through a true phase transition region, I will create some spatial correlations.
Yes.
And my simple question was now, if I particleize, if I translate my information of the fluid's elements into particle distributions, which according to Cooper-Frye is a single particle distribution, do I not lose information of this correlation?
You lose.
So is there any idea on the market of how to peak those things? Because, I mean, we are interested in these correlations, aren't we?
I'm not aware if anyone has tried, so somehow you just have to feed this information into your Cooper Fry, or create, if these are two-particle correlations, somehow you then have to fish out these two-particle correlations out of your fluid.
So the simplest way is just to include the particle momentum distributions F, which is assumed to be both the Einstein or Fermi-Dirac distribution, by the distribution which is not ideal gas distribution. Okay, and this is done in a sense partly if you have non-ideal hydro. Okay? So you include using these using deviations from the equilibrium distributions by, let's say, including the shear and bulk viscosity, which of course will enter to the Cooper Fry. So these correlations which you are telling, there should be also included by modifications of the particle momentum distribution.
You cannot. F is single particle distribution. Now we need to have two particle distribution to find correlations.
So for example, there was a work by Piotr.
They are included. I mean, if you expand them from the side of one particle, you will see this two particle correlation.
Then it depends exactly on what kind of correlations we are talking about.
So there is charge conservation, for example, which should be included, and this was done by Bożek. So they were probing the Cooper Fry formula, assuming that the particles have to be created in pairs. So this is a way to deal with it, but as I said, this is putting by hand.
And there are additional, and these are constraints on the particle momentum distribution. This is a certainly interesting issue for students, okay, because this is not really well still done. So this is a good subject to work on. How to go to this to hadrons from your fluid, okay, or from the core law plasma to the hadron system.
There may be other effects which are basically not included in hydro, and this, as far as I know, for now can be only put by hand. Final comment to this code is it's prepared in such a way that it includes, for now, only perfect fluid input. However, it's prepared in such a way that you can, in principle, easily extend it to put also corrections coming from viscosity. But it's not done. I was messing with the code, and I also did this, but for the anisotropic hydro, it is a different hydrodynamics.
All right, we still have actually a few minutes for a short.
I really suggest you to ask any stupid questions.
Now, there are no stupid questions in this, only stupid answers.
Yes. I have a chance.
Any questions?
If not,
Criticism? If not, let's have a short break, 10 minutes, and then we continue. Thank you very much for your attention.